So hey guys, welcome to the channel Learning Competitive Programming with CodeChef. So if you want to learn competitive programming and get a good hold on data structures and algorithm, this is the prime location for you. Every week there are several videos regarding various interesting concepts which will enhance your skills in DSN competitive programming as well as editorial videos of CodeChef contest. So if you are new to the channel, then please subscribe the channel and turn on the bell notification. Myself Chirayu Jain, I'm a CodeChef educator, and the topic that we're taking today is Quicksort. Okay guys, so now let us understand some of the basic things regarding the quicksort algorithm which we are going to take. Right, so first thing, quicksort is the highly efficient algorithm that we have today on sorting, right? And it is based on partitioning of the array into smaller arrays, right? So we'll see in the future things when we look at the examples and more technical definition that how do we exactly evaluate the array in quicksort. That is by using a pivot element and then partitioning the array on the basis of that smaller element should come before the pivot and the larger element should come after the pivot. So we'll see in that technical details about quicksort, but let's see some of the more interesting things regarding quicksort. So yes, as we have studied the merge sort, so if you have not watched the merge sort, then you can watch the merge sort as well. So like merge sort only, quicksort also comes into the category of divide and conquer algorithm, right? So it is also a divide and conquer algorithm, and quicksort was developed by Tony Hoare, right? So it was the name of the person who developed this, and this is the pic. So he developed the algorithm in 1959, right? So this is the time and the person who developed this algorithm. So these are some basic details that we should know while reading any of the stuff, right? So now let's get into the more systematic manner of what quicksort should do and what is the exact meaning of quicksort. So let's start with that. Okay guys, so now let's understand the quicksort algorithm in great detail, right? So as we have said in the introductory part as well, that it is based on the pivot element. So what exactly does this pivot element mean, right? So what is pivot element? Pivot element, it is the value which is assisting the splitting of the array, right? The splitting of the list. So this particular value determines that when a list is to be split and till what parts. Like for example, if I have this pivot value, this value will determine that at what position the split will happen and on which part, like the two parts that are created after the splits, these are the two segregated things, right? These are the two segregated parts, and for that we need to process it further, right? So this pivot value is the value which needs to be fixed in the array for its correct position, right? So the actual position for the pivot value belongs for which the pivot value belongs is called the split point, right? So actual position in which we are placing this pivot value is called the split point. So if the things are confusing for you, let's take an example and understand it properly, right? So first of all, the question arises that which value to take as the pivot value, right? So which value we should take. So you can take any value, that is like any starting value or any ending value. So here I am taking the ending value. You can also take the random value, or you can take the median as well, right? So anything you can take, but let's, for the clarity, I am taking this ending value as the pivot value. Okay, so now this 2 is the pivot for me, right? And I need to segregate this array into two parts by placing this pivot at its actual position, right? So how I should do that, right? So how do I know that this position is correct for this 2, right? So let me check from the starting, from here as well, right? So what I will do is, my strategy is that all the elements which are less than this pivot value should be before that, and all the elements which are greater than this pivot value should be on the right of that, right? So the smaller elements must be left of the pivot and the bigger elements must be at the right of the pivot. This is my thing. This is my point of understanding. This is my point of forming the approach, right? So let's start it from this very beginning, that is 8, right? So I'll make a pointer over here that will update that what values which what values are the values which are smaller than this particular pivot, right? So this is the pointer for that, and there is another pointer which will keep the track of the values which we are encountering, right? So let's say this is the one. So I compare 8 with 2, right? So when comparison with 2, so obviously 8 is greater than 2, right? So it cannot come before 2. So I'll move this black pointer to here now, right? So now the second thing is 7. 7 is also greater than 2, so that means it cannot come before 2. So I'll move the pointer to now. 6. 6 is also greater than 2, so it cannot come before 2. I'll move this pointer to now. 1. Now 1 is less than 2, right? So that means it should come before 2, right? It should come before 2. So what we will do, the pointer which we have made for this tracking of what are the elements which are less than 2, right? So this pointer and the pointer which we are encountering now for 1, right, we'll swap these values out, right? Because obviously since this value is greater than 2, so it should come after 2, and this value 1 is less than 2, so it should come before 2, obviously, right? So we'll swap out these values. So this value is swapped with this now. So what will be the final array after that? So the final array will be 1 7 6 8 0 9 2, since these two values are swapped, right? Swapped means the position of these two values are interchanged, right? Okay, so this is the outcome of from that. Now what will happen? What will happen? We have set the value for this index, right? For the first index, that means one value we have got which is less than 2, right? So if any other value exists, we'll keep updating it, right? So now we'll increment this particular blue pointer. We'll increment this particular blue pointer now. Why? Because let's say for this position, if we can find the value which is less than 2, since this value is already greater than 2, right? So let's see that if we can find any more value which is less than 2. And where is our black pointer? Black pointer is pointing at this position which is now swapped, right? This one, correct? So we have encountered that, right? Now let's move our black pointer to 0. Is this value less than 2? Of course it is less than 2. So again the swap will happen. We'll swap these two values. And after swapping, which is the final array that we'll get? That is 1 0 6 8 7 9 and 2. These two values are swapped. Okay, so this is the final array which we'll get after this swap, right? So where will be our blue pointer now? Since these two values are set, which is less than 2, now the blue pointer is pointing here. And where is a black pointer? Black pointer is at this position. We have already encountered this position, right? So we'll move till this position. 9 is not less than 2. 9 is not less than 2. So what we will do, we'll just move forward. So but after this, can we move forward? Because this is only the pivot value that we have chosen, right? So this is not something which we can like swap it out and compare with, right? So we have encountered all the elements in this, right? To fix the value of 2, we have encountered that all the elements in this. So what we encountered, there's these elements, right? These elements are smaller than 2 and these elements are larger than 2. No matter what the order is, it is not compulsory that 0 should come before 1 only. We are not maintaining any sorting order till now. We just want that all the elements which are less should come before this particular 2 and all the elements which are greater should come after this 2. That's all what we want, right? So we have done that. So now it's the time to place this pivot element at its correct position. So what is its correct position? This blue index, this blue pointer is its correct position, because we know that this pointer is indicating that these all values are smaller than 2 and from here it is larger than 2, right? So what we can do is we can swap this pivot value with this pointer. We will swap this pivot value, that is this last value, with this blue pointer to get to its actual position. So what will be the outcome for that? That is 1 0 2 8 7 9 6. So we'll swap out these values, right? So after swapping out, we can see that this is the correct position of 2. All the values are lesser than this 2, and this on the right hand side all the values are greater than 2. We got the correct position for 2, right? So that is the way in which this pivot element is fixed. Now this is not enough. This is not, you can see the sorted array that we got. This is not only the part. We have only fixed the value of this particular element, right? Now it's the time to solve out the same situation for these two subarrays as well, like this one and this one, because only this element is at its correct position. These elements are not at their correct positions, right? So what we will do, we'll again follow the partitioning algorithm for these two subarrays as well. So let's see what is the exact outcome after we do all the following steps. So let's see for these two subarrays. Okay, so for further processing, let's see, right? So we have fixed this value, that is the position of 2. Now we need to process the things for these two things, that is these two subarrays. We need to process the stuff, that how we can fix all of these positions. So let's start with this. Let's start with this part, right? So same process. The process will be same. We'll take the pivot, the last element as pivot, and then we'll start off with the comparison. So if we say 1 and 0 here, so there are 2 pointers. First one is this blue pointer and the black pointer, which is comparing everything with the pivot. So is 0 less than 1 or greater than 1? So right, obviously 1 is greater than 0, correct? So that means that it should come after this particular point, right? It should come after this, correct? So this is the greater element from the pivot element, so it should come on the right hand side, right? There is no element left in this subarray which is less than 0, correct? So what we will do, after incrementing this point, we know that it is pivot on the right, right? There is nothing, no more element which needs to be compared with this pivot element, right? So what we can do, we can simply do the swap of this pivot element with this blue index. Nothing else needs to be done. If it was smaller, then what we will do, we have just incremented this blue pointer as well, and the swap would return to the same element, to the same position only. Nothing would have been changed, right? But since this is greater element, so swap would happen, and we'll swap 0 with 1. So the following outcome will be 0 and 1, right? So these two things, like 1 and 0, are initially sorted out. So after this outcome, we can see that 0 and 1 are in correct position and 2 is in correct position. Now only the part left is to see this particular subarray, correct? So the same process, the process won't be changed. We'll select the pivot element here, that is the 6, the last element of the subarray that we are dealing with, right? And then what we will do, let's separate this thing out, okay, and start analyzing. 8, 7, 9, 6, where 6 is the pivot element. So now we'll take a blue pointer and a black pointer, right? And then we start the comparison. So is 8 less than 6? No. Is 7 less than 6? Right? So the black pointer is is updating, right? Is 7 less than 6? No. Is 9 less than 6? No. Right? So it's pivot element now. There are no more elements to compare with. So what we will do, we will swap the pivot element with this blue pointer. So now what the actual results we got, that is 6, 7, 9 and 8. We got the actual position of this element, correct? We got the actual position of this element. Now since this element is fixed, now our problem is to deal with this particular remaining part, that is 7, 9 and 8. We have to deal with this, right? So now let's start dealing with, we got the position of 6 as well, right? So the same process will repeat. We'll take the pivot element as the last element. This is the pivot, and now we'll take both blue and black pointers here and started comparing with this pivot element. So is 7 less than 8? Yes, 7 is less than 8, right? So what we will do, firstly we'll update the blue pointer, that is here. The blue pointer is updated here. But since before updating, what we are doing earlier, we are swapping the values of blue and black, right? We have seen earlier that how we will swap the values of blue and black. Since blue and black are at the same position, so the swap will not happen, or technically you can say the swap will be at the same position only, right? So swapping is done, it is at the same position, and we'll now update the black and the blue pointer. So the blue is also updated and the black is also updated, right? Is 9 less than 8? No, 9 is not less than 8, so we'll update only the black pointer, right? And we have reached the pivot element. So now what needs to be done? Only this pivot element is swapped with this blue pointer, right? So what we will do, we'll swap 8 with this blue pointer which is kept here, that is 7, 8 is here, and 9 will be at the last, right? So this is the actual position of this 8. This is the actual position of this 8, and there are two things left for the 7 and 9 as well, right? The 7 and 9, and here also if you see that there is one more thing left for the 1. So actually try using the same thing, like making this pivot and then comparing it to itself. It will be at this same position only, right? Because there are only discrete elements left, nothing to be compared of, right? So if we see the whole results, 2 was fixed, 0 and 1 is fixed, so 0, 1, 2, and then 6 is fixed for this position, then 7, 8 and 9. So the total outcome is 0, 1, 2, 6, 7, 8, 9 at their respective positions. So this is the sorted outcome that we are desiring for the given input array. This is the sorted array, right? This is the sorted array that we are wanting from the given input. So that's how we achieve this. That's how, by selecting the pivot and making this its position correct in the given array, we are finding out the final sorted array. So this is the whole idea behind the quicksort algorithm, right? So now we have understood with the help of example that what exactly quicksort algorithm means. Now it's the time to see the code of the quicksort algorithm and understand the code in detail. Okay guys, so now let us understand the code of the quicksort algorithm, right? So I've already written the code and I am writing this code on CodeChef IDE, correct? So now let's start from the same approach that we used to do in the previous videos as well, that starting from the main function, that what we are doing in the driver function, correct? So first of all, we are taking the value int n, that is denotes the number of elements that we have, right? So we'll input that and we'll make an array and input all the elements in that. Then I'm calling this quicksort function, right? So sort this particular array, and in that I am passing the array, the starting and the end index, like, and the output of this array, right? After that, if the after this function, the array will come in the sorted manner, so I'll output that, right? So this is the driver function. Now let's jump into the core algorithm, that is the quicksort function, right? So there are two functions similarly here also, like we have seen in the merge sort, but yeah, comparatively the code is bit less, right? And also quicksort is efficient, right? So in this function there are three inputs, that is the array, the starting index which is denoted by p, and the ending index which is denoted by r. So similar case, right, if p is less than r, right, this is the base condition that the starting index must be less than the ending index, right? So earlier what we used to, if we compare it from the merge sort, so firstly we used to recursively call the merge sort and then we used to call the core algorithm, right? But here, as you can see, firstly we are calling the partition algorithm. Why? Because in merge sort, if you have seen the previous video, that we are finding the mid first and then dividing the array according to that mid. But here we need to partition the array on the basis of the pivot element, the exact position where the pivot element is. So firstly we will call this partition function, and then we'll be knowing that okay, at this position the pivot element is placed. So let's say the position is temp here, right? So if the position is temp, then I need to recursively call the same function for the two subarrays which are left, as we have seen in the explanation also, right? So from the starting position p till temp minus 1, because at temp the position is fixed for the pivot element, till temp minus 1 I'll find the solution, and from temp plus 1 after the pivot element till the ending position r, I'll find the solution, right? So I'll make the recursive call on both of them, and let's say the recursive call will bring me the answer, because we have already satisfied the base condition, that is p is less than r. Now the main point is what is happening inside this partition algorithm, right? How we are finding the position of that pivot element. So that is always the logic that we have studied, just the implementation of that, right? Nothing else is done. So if we look at the partition algorithm, it also consumes three things, that is the array, the p and the r, right? The starting and the ending index, right? So let us understand step by step that what each of this thing is doing, right? It is a small code. Let us understand that what exactly it is doing. So first thing is to find that what is the pivot element. So the element which is present at the last index is the pivot element. We are taking it by convention, so you can take the first index as well or any random index as well, and settle the algorithm accordingly, right? So we are taking the last index. So let us say that this is the pivot element we have stored in the variable x. Now as we have seen that we are taking two things, the blue pointer and the black pointer, to match the element. So here this I denotes the blue pointer. This I denotes the blue pointer which we have understood, which keeps updating that okay, these till this point the elements are less than this pivot element, till this point the elements are less than pivot element, right? So we have initialized it with the starting index, that is p, correct? Now the black pointer comes into the picture, right? So this j is the black pointer, and then it keeps on updating, right, for each of the traversal from the p, right, starting from the starting index till the end index, right? So it keeps on updating, incrementing with 1. Now the condition is quite simple. If array of j, that means the array of black index that we black pointer that we are using, is less than or equal to x, that means the value is less than the pivot element, then what we will do, we'll swap up the black and the blue pointer. So what is the black pointer here? That is j, and the blue pointer is I, so we'll swap up that. Since j is already incrementing, so then nothing in the j, and we'll increment I in this condition only if we got an element which is less than x or equal to x. For the equal element we can just keep it, right? So if it is less than or equal to element, we'll just increment I, sorry. Okay, so this is the thing, right? We'll increment the I also, that is the blue pointer. So for all the elements we'll do this, and the same processing will happen for as we have seen in the example. And at last what we will do, the last step was to swap up the pivot element with the blue index, right? So what is the blue index? That was I, so we'll swap the blue index with the last element, that is the pivot element, that is at the last index present, right? So this is the final step that we are doing. And at last, what do we return? The partition index, right? The partition index. So what is the partition index? The blue pointer variable, right? That is I, so we will return I in that case. This is the simple clear cut. As we have studied in the example, the same solution is applicable here. Nothing else, nothing else need to be done, no extra like things involved and everything, right? So this is the simple core algorithm, the partition algorithm for the Quicksort, and we have seen that how the recursive thing is also happening over here, and how we are getting the index and then segregating the solution for the remaining two halves, right? So this is the whole code for the Quicksort algorithm. Let's try to run it on a sample. So let's say that if we are passing an array of size 4 and these are the elements, so the sorted order should come like 1 2 3 4, right? So if we run this, okay, so it's executed and the output is 1 2 3 4, right? This is the way we should code the Quicksort algorithm. Okay, so let us see the time complexity of the Quicksort. So for the best case scenario, there are two scenarios involved, right? For the best case scenario, if we consider, so after k steps we are able to reach this position, right? So like starting from n, if we divide it into a balanced partitions, right, that is equal partitions, so it must be like less than or equal to n by 2. It's also equal to less than or equal to n by 2. So the total work done will be n upon 2 to the power 1, because we are dividing into the equal partitions. We are taking the balanced situation over here. And similarly in the consecutive steps, if we follow the same approach, then at step number this, we'll find total work done will be n upon 2 to the power 2, right? Is this final step. So what will be the thing, that the total work done is n to the power n upon 2 to the power k, right, after k steps, right? Since it's at each step we are raising 2 to the power 1, at step number 2 to the power 2, after k step we have reached some this position, that it is n upon 2 to the power k, which is equal to 1, because we get a unique entity over this position, right? We get a final result over, like we get a final thing over this position, right? So when we equate this, so we'll get that k equals to log n. Similarly, right, by if we do the thing like 2 to the power k into 1 and take log both sides, so we'll get that k will be equal to log n. K will be equal to log n on the base 2, right? So this is the thing for the best case scenario in which we are dividing the array into the some balanced partitions, right? But there can be a case in which, let's say that there are n possible things, right, n possible members which is to sort, and at this position 1 only this element is sorted and rest n of the n minus 1 elements are remaining, right? Only the first position is sorted and let's say n minus 1 needs to be done. Similarly, for the same case, if we have one successful count here, then n minus 2 cases needs to be solved. Similarly, it will progress, right? So at each step you can see there are work done that n minus 1, n minus 2, and it will proceed to the time complexity will be plus n minus 2 till 1, which leads to be the solution to order of n square, right? So if you sum all of these, so it will be the polynomial form of power 2, right? So this is the worst case in which we are taking only one element, and then the solution comes out to be solve the remaining elements, right? The remaining thing needs to be sorted out, right? This is the unbalanced partition. What type of partition it is? It is the unbalanced partition. This is the balanced type of partition. Okay, so we have seen the time complexity can vary in the best case and the worst case. So that this worst case is very rare, right? So if we take very big arrays and then just try to get our things done for the sorting thing, so that can be a little costly for us. That's why we use, for the big arrays, we use merge sort. That is quite optimal for that. And for the smaller arrays, we generally prefer the quicksort algorithm, right? So this is the overall thing about the time complexity, right? And as space complexity is considered for the balanced portion, the space complexity is order of log n, because we can see that the tree is quite balanced. And if we see this unbalanced partition, so the space complexity will be varied to order of n, right? So these are the differences between the time and the space complexity for the quicksort algorithm.